Hi, I'm Jodie Lutkenhaus in the Artie McFerrin Department of Chemical Engineering at Texas A&M University, and in my lab we're working on how thin films respond to temperature. Thin films can be coatings that are 100 nanometers or less in thickness. That's far thinner than a human hair, and they can be used in applications such as food packaging, coatings for lenses, optical coatings, and so on. And they can have really fascinating properties because they're so much thinner than what we usually work with. Thin films have a lot of exciting applications that people are working on. For instance, one application could be a functional coating on a hip implant, for example, where the coating could deliver a drug to help you heal after the surgery. And another application would be in the area of smart coatings for windows. Imagine you have a window and you could just press a button and it could automatically tint up and block heat to keep your room cool. It's important to know how these thin films respond to temperature because depending on the temperature, they could melt, soften, or crack. And depending on the application, that could make or break the application. Now, to measure those properties in a thin film is very hard because you don't have a lot of the material. And in my lab, I'm really excited because we've just developed a way to measure how these films respond to temperature for the thinnest of films, less than 100 nanometers thick. Our system works on principles very similar to the quartz crystal in your watch. The quartz crystal in your watch vibrates with a resonant frequency that keeps time. And we have a similar quartz crystal here. And what we do is we add a coating to the quartz crystal, and that's going to be our thin film. And it's going to vibrate at a different resonant frequency because that coating is slowing it down. And the vibration is going to dissipate, and that tells you the mechanical properties, how fast it dissipates. And that's going to change with temperature. So we put a coating on the crystal, we measure how it vibrates and dissipates, and we put the crystal in this chamber, which is called a quartz crystal microbalance with dissipation. We change the temperature and we measure those properties. And when the film melts or softens, we can measure all of that in this little chamber. Now that we have this system in place, we can measure these thermal changes in thin films, and then we can use that to predict when thin films are going to fail when they're being used. On the other hand, we can also design films that respond to temperature at a given temperature we want, and we could use that to make temperature responsive films that deliver drugs at a given temperature or kind of signal to us when something's happening.